Hello students, today in this session we are going to continue with the unit 8, the D block and F block elements. So first here we are going to see what are the D block elements. Okay, the D block elements are the elements of the periodic table from the group number 13 to 12. Okay, from the group number 13 to 12, which have the property that the valence electron is present in the d orbitals of that atoms. Okay, the f block elements are the elements from the group number 3 to 12 only, but they are separated due to their radioactive nature and also containing f orbitals. Okay, they are containing 4 f orbital and 5 f orbitals, which are progressively filled in the latter two long periods. These elements are formal members of group number 3, from which they have been taken out to form a separate f block, which you see generally in your periodic table as the lanthanides and actinides. Okay, in the there are mainly three series in the transition elements. Okay, there are mainly three series in the transition elements or d block elements. They are namely the 3d series, okay, which is scandium to zinc series, the 4d series, okay, which is the 4d series, which is yttrium to cadmium, okay, and the 5d series, which is lanthanium to mercury. Here the middle elements, which are selenium to leutherium, okay, selenium to leutherium, are been removed as they are the as they are containing the f block, f suborbitals. Therefore they are kept in the f block. Okay, they are regarded as the f block elements. The next is the fourth 6d series. Okay, fourth 6d series, which being actinium is still incomplete. Okay, is still incomplete in your course, but presently the elements has been added there. Okay, presently the elements has been added there, and 6d series is also present. Okay, next, the f orbitals are also known as the inner transition metals. Okay, the f orbitals, the two series of the f orbitals are also known as the inner transition elements, and their other name is lanthanides and actinides. Okay, their other name is lanthanides and actinides. What are transition elements? If I am going to define the transition elements, then what are the transition elements? Okay, so the transition elements are the elements which has incompletely filled d orbital in its ground state. Okay, in its ground state, it is having incompletely filled d orbitals, or in any one of its oxidation state. Okay, but zinc, cadmium and mercury of the group 12 have full d10 orbitals in their electronic configuration in their ground state as well as in their common oxidation states, and hence they are not regarded as the transition elements. It means that if I am going to see in the series, okay, if I am going to see in the series, as you can see here the scandium, titanium, nickel, copper, okay, these all are regarded as the transition element, but when we talk about zinc, they are not considered as the transition element due to their fully filled d orbital, they are fully filled d orbitals. Okay, but you will see that copper is also having fully filled d orbital, but this fulfilled d orbital is after that one electron is been taken up from the 4s orbital here. Okay, so it means that the transition has taken place here in order to complete its higher energy d orbital. So therefore it is also considered, copper is also considered as a transition element only. But in case of zinc, no transiting element will be, no transition of element will be there. No transition of elements will be there in the case of d orbital, between the d orbital and the 4s orbital. Okay, here. Similarly, this thing is also seen in cadmium case also. It is also having the fully filled d orbital. Okay, fully filled d orbital. Therefore, it is also not considered as the it is not considered as the transition element. Okay, similar properties applied for the mercury also. Okay, now let's coming to the series after the transition elements definition. Also, one more thing which I would like to add here is that the general electronic configuration for the d orbital is n-1 d. The electrons which can be filled up in D is from 1 to 10. Okay, and ns1 to 2, ns1 to 2. Okay, so this is the general electronic configuration for the D block element. Let's move further here and see what are the series present here. So the first series of the D block element is scandium series. Okay, is the scandium series. Here scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc is there. Okay, yeah, you can remember this series by the name science teacher is very cruel, mange fees, cobalt, nickel, copper, zinc. Okay, so here this is the trick by which you can remember it. Science teacher is very cruel, mange fees, cobalt, nickel, copper, zinc. Okay, so here the scandium is having the electronic configuration of 21. Okay, sorry, not the atomic number of 21. So its electronic configuration becomes argon 4s2, then then 3d1. Okay, like this, one electron will be increased in every successive element here. Okay, and at last in zinc the 3d orbital will be fully filled. Okay, the in the at last the zinc orbital will be having a 3D fulfilled orbital here. Okay, next here two special cases are there in the case of chromium and in the case of copper. Okay, in the case of chromium and in the case of copper, here we can see that they are containing only one electrons in their 4s orbitals. Okay, this the reason here is that when we are writing the electronic configuration for chromium here. Okay, when we are writing the electronic configuration for chromium here, then we will see that it will be having 3d4 4s2. Okay, 3d4 4s2. But as one vacant orbital is present in the d orbital in the case of chromium here. Okay, so here what will happen, we will make that vacant orbital half filled by transiting an 4s electron. Okay, by transiting an 4s electron in order to make this atom more stable. Okay, similarly in the case of copper here, the 3d9 configuration will be there for d orbital. Okay, 9 electrons will be present there. So one electron will be transit from the s orbital to the d orbital and it will fulfill itself in order to attain the stability. Okay, next series is the yttrium series. Next series is the yttrium series. Okay, yttrium, zirconium, okay, niobium, molybdenum, technetium, ruthium, rhodium, palladium, silver, cadmium. Okay, these are the second series elements. These are the second series elements. Here, yttrium is having electronic configuration of 39. Okay, so therefore they will be having the electronic configuration of krypton 4d1 5s2. Okay, 4d1 5s2. Similarly, when moving further here, one electron will be added in their 4d orbitals till the 4d orbital is fulfilled. But here three special cases are there. Okay, three special cases are there. In case of sorry, two special cases are there. One is the one is the palladium. One is the palladium. Here you can see that palladium has transited two electrons from their 6d 5s orbital, okay, 5s orbital, and fulfilled their d orbital and fulfilled their d orbital. Due to this property of palladium, they are used as very good, they are used as very good catalyst for hydrogenation purpose, okay, for hydrogenation purpose, for the reaction with hydrogen or addition of hydrogen in a compound. It is used due to their this property only, because they are having the property that they have vacanted their 5s orbital, and which makes a place for electrons of the hydrogen atoms in order to shift their electrons for some time, and they act as palladium act as a very good catalyst here. Next, in the case of silver, here you can see from 5s orbital one electron has been transited to the 4d orbital in order to complete the d orbital, okay, in order to complete the 10 electrons in the d orbitals, and hence it also has a fulfilled d orbital. Next, in the case of cadmium, it naturally has fulfilled d orbital because its electronic configuration is 48, and it attains the full d orbital, 4d orbital has been full 10 electrons here, okay. So hence cadmium cannot be considered as a transition element here, okay. Next is the Lathium series. Okay. Next is the Lathium series. Here, La Hafta. Okay. Varna, Rahman, Usman, Irfan. पीटेंगे और हॉस्पिटल पहुंचा देंगे, like this you can remember it, okay. And here from electronic configuration, the atomic number starts from 57, okay, and it continues till 80, but here is a small gap, here is a gap between 57 to 72, which are the F block elements which has been separated from here, okay. Similarly in the actinium series also you can see that after 89 104 is the next element here, okay, in this series. So the middle elements, the left out 14 middle elements are been taken into the next series, which is next block, which is known as the F block elements here, okay. So here also two special cases are there where gold is having full filled d orbital, okay, and only one electron in there, and only one electron in there, um, 5s out 6s outermost shell, okay, 6s outermost shell. And similarly in the case of platinum, here you can see that as 8 electrons were present here, so one electron is being transited to the d orbital from the s orbital, okay, in the case of platinum here, okay. Next 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 is the actinium series, okay. Next is the actinium series, where actinium, rutherfordium, dubstadium, okay, dubstabium and okay, dubstanium, and all these elements are present here. Here the electronic configuration starts from 89, then 104, 105, and the electrons in the 6d orbitals 1 2 3 4 like this is increasing, okay, and at last it is 10 in the Röntgen, okay, it is 10 in the Röntgen by transiting one electron from the 7s orbital to the 6d orbital here, okay. Let's move further here. A question is asking here, on what ground can you say that scandium is a transition element but zinc is not? So I have mentioned this before only, that as a scandium is having half-filled d orbital, which can help in the transition of electrons from the s orbital to the inner d orbital. But in the case of zinc, this is not possible, as its d orbital is fully filled and no electron transition will be seen in their ground state, okay. So hence not in ground state, or also in its oxidized state also, okay, because only 2 plus is the oxidation state, oxidized state of zinc, and it will be removed from, and it will be only removed from the outermost orbital only, okay. So hence we can say that the zinc is not a transition element here. Next, moving further, here a question is asking that silver atom has completely filled the orbital 4d10 in its ground state. Can you say that it is a transition element? So here, if I am talking about silver here, so silver is having only one electron present in its s orbital. So the two orbitals from the 5s orbital, out of which one is electron has been transited to the d block of the 4d block in order to complete its d block. Okay, so yes, it is a transition element only. Okay, it is a transition element only due to the transition of electrons from the 5s orbital to the 4d orbital here in its ground state. Now, what are the physical properties of the D block elements? So, here nearly all the transition element display typically metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, metallic luster, with the exception of zinc, cadmium, mercury, and manganese. Okay, they have one or more typical metallic structure at normal temperatures. Okay, which are these elements which are having more than one typical metallic structure? They are zinc, cadmium, mercury, and manganese. Okay, so in the case if I am seeing that which kind of lattice structure they are forming, so scandium is forming HCP. Okay, scandium is forming HCP, which is hexagonal close packing. Okay, then hexagon yttrium is also forming hexagonal close packing, while lanthanum is also forming hexagonal close packing. But they can also exhibit the body centered cubic. Okay, body centered cubic. Next, hexagonal close packing is also seen by titanium, zirconium, and hafnium. Vanadium, niobium, and niobium and tantalum, all they are possessing body centered cubic cells. Okay. Next, chromium, molybdenum, and tungsten. Chromium, molybdenum, tungsten are having body centered cubic cell. But in case of chromium, cubic close packing can also be seen. Okay. In case of magnesium, X, it shows that one or more different metallic structure or one or more different metallic structures can be seen here. Okay. Next, in case of technetium, it is hexagonal close packing. In case of in case of radium, hexagonal close packing is there. Okay. Then next comes the iron, body centered cubic. Okay. Ruthenium, hexagonal close packing. Osmium, hexagonal close packing. Cobalt, cubic close packing. Rhodium, cubic close packing. Iridium, cubic close packing. Nickel, cubic close packing. Palladium, cubic close packing. Platinum, cubic close packing. Copper, CCP, CCP, CCP. Okay, copper, silver, and gold are having cubic close packed structure. Okay, but zinc, cadmium, and mercury with manganese are having more than one metallic structure. Now, let's talk about the trends in the melting point of the transition elements. Okay, trends in the melting point of the transition elements. So, the transition metals, with the exception of zinc, cadmium, and mercury, are very much hard and have low volatility. Okay, and have low volatility. Their melting point and boiling point are shown here in the left side with the graph. The melting point of 3D, 4D, and 5D transition metals, okay, the melting point of their melting point are high. Okay, their melting point are high, which are been depicted here. Okay, the high melting point of these elements are attributed to the involvement of greater number of electrons from the n-1 d in addition to the ns electron in the interatomic metallic bonding. Alright, okay. In any row, the melting point of this element rise to a maximum at d5. Okay, you can see that at d5 means in the case of tungsten, Okay, in the case of tungsten, in case of molybdenum, and in case of chromium, we can see that it has been rising, except for anomalous values of manganese and technetium. Okay, manganese and technetium, if we are leaving that, but in the case of D5, we have seen that the temperature, the melting point rises in the case of D5, or it means that half-filled d orbitals. Okay, fully half-filled d orbitals. The They have high enthalpies of atomization. Okay, they also have high enthalpies of atomization, which is shown in the next graph. I will show you further that the maxima at about the middle of each series indicates that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electron, stronger is the resultant bonding. Okay, in general, the greater the number of valence electrons, stronger is the resultant bonding, since the standard enthalpy of atomization is an important factor in determining the standard electrode potential of metals with high enthalpy or atomization. Very high boiling point tends to be noble in their reaction. Okay, they will be having very high boiling point also if they are having very high atomization enthalpies. Okay. Another generalization that may be drawn here is that the metals of the second and third series have greater enthalpies of atomization than the corresponding first series. Okay, then the corresponding first series, the second and third series of the transition elements are having more atomization enthalpies. This is an important factor in accounting the occurrence of more than frequent metal-metal bonding in compounds of heavy transition elements. Okay, we can see metal-metal bondings between the higher heavy transition elements. Okay, between the heavy transition elements, due to this reason only, due to higher atomization. Okay, due to the higher atomization. So here we can see that the first series is having very low energy of atomization. Okay, very low atomization enthalpy. But while in case of third and fourth series, it is very high. Now, what is the variation in the atomic and ionic size of the transition metals? In general, ions of the same charge in a given series shows progressive decrease in the radius and increase in the atomic number. Okay, with the increase in the atomic number, there is a progressive decrease in the radius of the atom. Okay, this is because the new electron enters d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron. Okay, this shielding effect is also very important part here. Realize that the shielding effect of d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases, and the ionic radius, what happens, it decreases gradually. Okay, it decreases gradually. The same trend is observed in the atomic radii of the given series. Okay, in the given series, and the variation within a series is quite small. Okay, we cannot see very much high variation in case of radius here. Okay, an interesting point emerges with when atomic sizes of one series are compared with those of the corresponding element in the other series. The curve in the below diagram, I will going to show you in the next part. Okay, shows an increase from the first 3D to the second 4D series. Okay, first 3D to the second 4D series. Okay, and same as those of the corresponding members of the second series. This phenomenon is associated with the invention of the 4f orbital, which must be filled before the 5D series of elements being. The filling of 4f before 5D orbital result in a regular decrease in atomic radii called lengthenide contraction. Okay, lengthenide contraction, which essentially compensates for the expected. Okay, which essentially compensates for the expected increase in the atomic size with the increasing atomic number. The net result of the lengthenide contraction is that the second part of the third D series, okay, second part of the third D series uh, exhibits similar radii, and have very similar physical and chemical properties, much more than expected on the basis of the usual family relationship. Okay. Now here in this trend in atomic radii, okay, we can see that the radius is gradually decreasing, and at a point it is been increased out in the last element case. Okay, in the last element case it is been increased. Okay, so this is due to the shielding effect of D. Okay, this is due to the presence of shielding effect of D. The decrease in metallic radius coupled with the increase in atomic mass results in a general increase in the density of these elements. Okay, here these elements are very highly dense. Okay, they are very highly dense. Thus, for titanium to copper, the significant increase in the density may be noted. Okay, for the first series, the significant increase in the density may be noted here. Okay, here are some of the properties which are been given for your first series element, which is scandium, titanium, vanadium, chromium, manganese, iron, copper, nickel, zinc. Okay, you can read it out. All the properties are given out here. The properties are atomic number, their electronic configuration, then enthalpy of atomization is also provided here. In ionization enthalpy, okay, so the ionization enthalpy is been provided here in the case in the form of first ionization enthalpy, second, okay, and third. First ionization enthalpy means the energy required to remove first electron. Second ionization enthalpy means the energy required to remove the second electron, and third ionization energy means the energy required to remove the third electron from the valence shell. Okay, next is the metallic and ionic radii, which is given in picometers, the standard electrode potential for the first series of the d block elements. Okay, next, here a question is asking that why do the transition elements exhibit higher enthalpies of atomization? Because of the large number of unpaired electrons in their atom, they have stronger interatomic interaction. Okay, they have stronger interatomic interaction, and hence stronger bonding between atoms, resulting in their higher enthalpies of atomization. Okay. Here, the next question is asking here that in the series scandium to zinc, the enthalpies of atomization of zinc is lowest. Why? Because it is having full d orbital, and due to lower shielding effect of d. Okay, due to lower shielding effect of d, we can see that the enthalpy of atomization is very low for that zinc. Okay, due to fulfilled d orbital. Next, ionization enthalpies. Due to increase in the nuclear charge, which accompanies in the filling of the inner d orbital, there is an increase in the ionization enthalpies along each series of the transition elements from left to right. However, many small variations are shown in the table. Okay, in the above table gives the values for the first three ionization enthalpies of the first row elements. These values shows that the successive enthalpies of these elements do not increase as steeply as in the main group elements. Okay, in the main group elements we have seen that the ionization enthalpy is steeply increasing, but in the case of the transition metals, it is it is not very steep. It is a curve like shape, but not very steep. Okay, although the first ionization enthalpy in general increases, the magnitude of the increase in the second ionization enthalpies for the successive element is much higher than in the case of their successive, in the case of their preceding. Okay, the irregular trends in the first ionization enthalpy or of the 3D elements, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3D orbitals. So, the unipositive ions have d 11, okay, d n configuration with no 4s electrons. Okay, with no 4s electron, there is thus a reorganization energy accompanying ionization, which with some gains in exchange energy as the number of electron increases and from the transfer of s electrons into the d orbital. Okay, what happens here when d orbital removes electrons here? Okay, so or it is lacking the fulfillment of the electrons and they are having vacant orbitals, then the 4s orbitals electrons are being replaced. Okay, it has been transited here. Due to this, some gains in the exchange energy is also present here. Okay, some gain in the exchange energy is also present here, and it it increases, and from the transfer of s or electrons into d orbital, there is the generally expected increasing trends in the values, and the effective nuclear charge increases. However, the value of the chromium is lower because of the absence of any exchange in the D configuration, and value for zinc higher because it represents an ionization from the 4s level. Okay, as 4s, the zinc will be removing its electron from the 4s. Okay, it will be removing very readily its electron from the 4s orbital. Okay, the lowest common oxidation state of the metals in the D block is +2 to form M2 plus ion from the gaseous state atom. Okay, the sum of the first and the second ionization energies is required in addition to the enthalpy of the atomization of each element here. Okay, the dominant term is the second ionization enthalpy, which shows usually high values in the, okay, high values for chromium, copper. Okay, for chromium, copper, where half-filled or full-filled d orbitals are present, and they ions are disrupted here with consideration loss of exchange energy. Okay, here due to the transition of elements from the between the s block and the d block, here considerable loss of exchange energy is present here. The value for zinc is correspondingly low, as the ionization consists of the removal of an electron, which allows the production of the stable d10 configuration. Okay, stable d10 configuration here, which is 3d10 configuration in the case of zinc here. The trend in the third ionization enthalpies is not complicated by the 4s orbital factor, and shows the greater difficulty of removing an electron from the d5 in case of Mn2 plus and d10 in case of Zn2 plus ions. Okay, superimposed upon the general increasing trends, in general for the third ionization enthalpies are quite high, and there is a marked break between the values of Mn2 plus and Fe2 plus. Also high values for copper, nickel, zinc indicates why it is difficult to obtain oxidation state higher greater than that 2 plus. Okay, 2 plus in these elements. Although ionization enthalpies give, okay, although ionization enthalpies gives the some guidance concerning about the relative stabilities of the oxidation states. This problem is very complex and not amendable in the generalization method. Okay, in the generalization process. If I'm talking about the oxidation states here, so one of the notable features of the transition elements is that it has great varieties of the oxidation state. Okay, it has great variety of the oxidation state. Here below you can see that in this table, scandium is possessing +3 oxidation state. Okay, because all the three electrons present in its third shell will be removed out here to attain a +3 oxidation state here. But in case of titanium, +2, +3, +4, three valencies can be seen out, three oxidation states can be seen out. Okay, so here the +4 oxidation state for titanium is very common. Okay, it is very common. In similarly, in case of vanadium, +5 valency is very common. Okay, +5 valency is common, but it can possess +2, +3, +4, or +5. Four oxidation states are possible for vanadium. In case of chromium, five oxidation states are there: +2, +3, +4, +5, +6, in which +6 and +3 are common. Okay, +6 and +3 are common. Similarly, in case of manganese, six oxidation states are there, out of which +2 is very common, but in some cases it is seen that +7 is also a very common oxidation state for manganese. Next, iron. For iron, +2 and +3 are the common oxidation states. Okay, but it can possess a +4 oxidation state also, and +6 oxidation state also in very cases, in some of the cases. Next, cobalt, +2 and +3 are the common oxidation states for it. In nickel, +2, in copper, +2, and in zinc, +2 is the common oxidation states. Okay, so here the trend we can see that first the oxidation state is increasing, and then it is decreasing gradually from manganese. Okay, from manganese. As we can see that till coming to manganese, the oxidation state is increasing, and when we are going further far from manganese, we can see that it has been decreasing to +2 here. Okay, so this is the oxidation state trend for the first series of the D block elements. Name, question is asking here, name a transition element which does not exhibit variable oxidation state. Okay, so here the answer is zinc and scandium. Okay, zinc and scandium. They will not possess variable. They will not possess um, variable oxidation states. Okay, they will not possess variable oxidation states. Next is the trends in electrode potential. Okay, trends in the electrode potential. So, what is the trends in the electrode potential? The unique here we can see that the electrode potential values when plotted in the graph here. So here cobalt, nickel, okay, cobalt and nickel are having different property here. Okay, are having different property here as comparison to the other elements. Okay, in the present in the series, but here copper, okay, in the case of copper, the copper has a unique behavior of having a positive electrode potential, accounts for its inability to liberate H2 from acids. Okay, it cannot liberate H2 gas from acids. Only oxidizing acids such as nitric and hot concentrated sulfuric acid reacts with copper. The acids being reduced, the high energy or to transform copper solid to copper 2 plus aqueous is not balanced by its hydration enthalpy. Okay, the general trends towards less negative values across the series is related to the general increase in the sum of the first ionization enthalpy and the second ionization enthalpy. It is interesting to note that the value of electrode potential for manganese, nickel, and zinc are more negative than the expected from the trend. Okay, they are more negative. Okay, copper, nickel, okay, cobalt, nickel, and zinc are more negative as comparison to that the trend which we are following here. Okay, why chromium 3 plus reducing and Mn5 plus oxidizing when both have D4 configuration here? A question is asked here. So the answer will be that chromium 2 plus is reducing as its configuration changes from D4 to D5. Okay, therefore it is reducing. While the latter having a half-filled T T2G energy level. Okay, T2G energy level. On the other hand, the change from Mn3 plus and Mn2 plus result in the half-filled D5 configuration, which has extra stability. Okay, which has extra stability, and hence it is acting as an oxidizing agent. Mn2 plus is 5 plus is oxidizing agent, while Mn3 plus is oxidizing agent, while chromium 2 plus is a reducing agent. Okay. If we see the formation of halides with the 3D metals, 3D series metals, so here we can see that they can form, titanium can form tetrahalides, okay, pentahalides, and dihalides. Okay, while vanadium, while in case of vanadium we can see that it can form pentahalides also. Okay, it can also form pentahalides, trihalides, tetrahalides, and pentahalides. Chromium can form hexafluorocompounds. Okay, hexafluorocompounds and pentafluorocompounds, while it can form tetrahalide, trihalides, and dihalide compounds. Manganese can form tetrafluoro and trifluorocompounds, but generally manganese is forming dihalide compounds here. Okay, dihalide compounds here. Next is the iron. Iron can form trihalides and dihalide compounds. Okay, FeCl3, FeCl2, FeBr3, FeBr2, like these compounds are generally seen for iron. Cobalt can form trifluoride, okay, trifluoride, and it can form dihalides, okay, dihalides. Nickel can form dihalides. Copper can form copper can form if when oxidation state for copper is +2, then it can form dihalides, but when its oxidation state is 3, which is known as cupric condition, so in cupric halides are formed out, having only one halogen here. Okay, the last zinc is also having dihalide formation tendency. Okay, dihalide formation tendency. So here this is for the uh, 3D series elements, and they are generally When a magnetic field is applied to substances, mainly two types of magnetic behaviors are seen. One is diamagnetic and one is paramagnetic. Okay, so the diamagnetic substances are the substances which are repelled away by the magnetic field, and the paramagnetic substances are the substances which are attracted by the magnetic field. Okay, so in the case of 3D element here, in the case of 3D element here, we can see that they are having variable nature. Okay, they are having variable nature towards their paramagnetic or diamagnetic nature. Okay, paramagnetic nature arises due to unpaired electrons. Okay, unpaired electrons. But in case of 3D element here, in case of 3D series here, ferromagnetism is also present. Okay, in iron, cobalt, and nickel. Okay, in iron, cobalt, and nickel, we can see that ferromagnetism, where strong attraction is seen between iron, cobalt, and nickel for the magnet. Okay, for the magnet, we can see strong attraction. Okay, strong attraction. Okay, and this paramagnetism depends on the paired and unpaired electrons. Okay, paired and unpaired electrons present in the atoms. Okay, present in the atoms. If someone want to find out the magnetron's value here, so it can be find out by this formula for any element. The formula is here: mu is equals to under root n, n plus 2, where n is the number of unpaired electron. Okay, where n is the number of unpaired electron. So here a question is asked here: calculate the magnetic moment of a divalent ion in aqueous solution if its atomic number is 25. Okay, atomic number is given here as 25. So the electronic configuration will be form of that D5. How many elements will be present there? D5. Okay, D5 elements will be present there. Electrons will be present there. So the value for n is here is 5. So here the formula becomes mu is equals to under root 5 plus 2 into 5 plus 2. So the value for the magnetic magnetron will be become 5.92 Bohr magnetron. Okay, 5.92 Bohr magnetron. If same is asked for 27, then try to calculate here. Here the outermost element, the valence electrons will be 7. Okay. Also, the colored compounds are formed by 3D series. Okay, so what colored compounds are formed by 3D series? Scandium, titanium, scandium does not form any colored compound. Titanium 4 plus does not form any colored compound, but titanium 3 plus will form colored compounds here. Okay, 3 plus will form colored compounds here. Okay, and the color will be purple, and the color will be purple. Next, vanadium 4 plus forms blue, vanadium 3 plus forms green, vanadium 2 plus form violet, chromium 3 plus forms violet, manganese 3 plus forms violet, chromium 2 plus form blue, manganese 2 plus form pink color, ferrous 3 plus forms yellow color. Okay, ferric condition forms yellow color, ferrous Fe2 plus forms green color. Okay, Fe2 plus forms green color, cobalt 2 plus and 3 plus forms blue pink color. Okay, nickel 2 plus form green color, copper 2 plus form blue colors, and zinc forms colorless compound. Okay, zinc, scandium, and titanium forms colorless compounds. Here, the D block element, the 3D block elements, the 3D series elements have a greater tendency to form the complex compounds here. Okay, they can form complex compounds, which we have studied in the previous chapter of the coordination chemistry. Okay, in the previous sessions, I have discussed about the coordination chemistry. So there you can see that we have discussed about the complex compounds, which are generally formed by the 3D series elements only. Okay, as I have told you about the catalytic properties, so here the transition metals and their compounds are known for their catalytic property, out of which vanadium is one of the major catalyst. Okay, major catalyst. Vanadium, copper, they are generally used as catalyst. Okay, in many of the reactions, due to the nature of their interstitial compound formation, they are formed very small atoms like hydrogen, and nitrogens are trapped in their crystal lattice of the metals. They are usually non-stoichiometric and are neither typically ionic or nor covalent. Okay, so due to this reason, they are having very high melting point, higher than that of the pure metals. They have very hard. Some boroids approach diamond in hardness. Okay, one of the boroids has the hardness more than that of the diamond. Okay, they retain their metallic conductivity. They are chemically inert. The interstitial compounds are chemically inert. Okay, they can form alloys. They can form alloys when two or more metals from the 3D series are mixed together. They can form alloys. As some examples are brass, which is the alloy of copper and zinc; bronze, which is the alloy of copper and tin. Okay, so like this, alloys can be formed out where also molybdenum, steel, chromium, and vanadium, etc., are added to the iron in order to obtain steels and stainless steels. Okay, so like these alloys are also formed out, which is also a unique property for the 3D series elements. Okay, 3D series elements. So this is for this session. We will continue the chapters next part in the next session. So thank you.